is. Okay, so here's kind of the idea is you've done lots of integrals now. You've learned all kinds of integrals. And so what we're going to be looking at now is the idea of an improper integral. And there's really two things we look at. Generally, what you guys have always done is the interval of integration has been finite. So what I mean by that would be like, as an example, you're integrating from 2 to 4. Okay, these things have always just been finite numbers. You're always just some specific interval like that. You've always done that. Okay, what you have not done yet is you have not done something like this, 0 to infinity, f of x dx. Okay, so you can do an integral where the boundaries of the limits of integration are unbounded. Okay, they might go to infinity. You also might go negative infinity to infinity, like that. You can do that. Okay, so that's one idea. The other thing is that you've looked at is the function has always been bounded. So you've always done a definite integral when the function is bounded. What I mean by this is, like in this region here, the upper boundary is the curve. The lower boundary is the x-axis. Then you have this boundary here and this boundary here, right? So this region in here is bounded. All of your integrals have been that way. Now what's different is, you haven't looked at anything like this yet, but you could look at something like this, and we will, is let's say that you had a function that was doing something like this. It was approaching an asymptote, like that. And let's say that you were going to integrate from 0 to infinity, or even 0 to 10, something like that. This region under this curve would be unbounded, and the reason is because that thing goes forever, doesn't it? Okay, so you haven't looked at that yet, so that's kind of what we look at in an improper integral, is either the limits have got an infinity in there somewhere, or the region that you're considering is going to infinity because maybe of a vertical asymptote or something. That's the idea. That's what we mean by an improper integral. Okay, so what we're going to look at as we begin to go through this is we're going to focus on this thing first. We're going to look at the integral of integration is infinite. So like I just said, an improper integral, you're either going to have the limits of integration are infinite, or you're going to have this unbounded case like I showed there. You're going to have something around an asymptote. That's the idea. Okay, so let's look at this first example here, and this gets into some pretty interesting ideas that I think you'll find interesting anyway. I hope so. Okay. So this one we're integrating from 0 to infinity, 1 over x squared, and this one is a mistake. I had a mistake on here too that you guys need to change. That is not a 0. That was intended to be 1 to infinity, 1 over x squared dx. Do you guys know why that's a mistake? The function's undefined at 0, right? Okay, so you're not going to integrate on a boundary where that's undefined. 1 over 0 is undefined, so that's a mistake, so be sure to correct that. Okay, on this one, the interval of integration, which is talking about this, that is unbounded. So you want to write that down. So what we're looking at is an unbounded interval. If you look at your graph, and I think I provided you a graph on here, what we're doing is we're integrating now from 1 to infinity. So you're looking at this little region right here. All right? Now that thing right there is bounded. The integrand is bounded. And what I mean by that is, if you look at that region from 1 to infinity, it's bounded. On top there's a curve, right? Okay, the x-axis is below, and then there's a 1 right there. Now that thing does go on forever, but we're bounded above, below, like that. Okay, so it's not like we don't have a vertical asymptote going to infinity. We have a horizontal asymptote, but that's okay. So what we're going to do is we're going to look at how you would figure this out. Now, at first glance, a student would probably think, and if I was learning this for the first time, my thought process might be, well, that area under that curve's infinite, okay, because it goes on infinitely. That's not necessarily the case. Sometimes that thing will converge to some precise value, okay, even though that region goes on forever. And that's pretty abstract, and that seems like a strange idea, but a lot of times you get a finite answer even though there's an area that's going on infinitely. That curve's going on infinitely. That's kind of weird, isn't it? So the idea, what you're going to do with this is we're going to set this up like this. The first thing we're going to go ahead and do, let's just go ahead and write down the integral, 1 to infinity, 1 over x squared times dx. And what we typically do is we use a variable and we change this infinity. So what we typically do, I'm just going to follow the book. They tend to use the letter b, which is okay. So I'm going to change that to 1 over x squared dx like that. And then we're going to go ahead and do that integral. So I'm just making a change. And let's do that first of all. Now we can do the integral of 1 over x squared dx from 1 to b. We're going to go ahead and do that. So let's go ahead and do that integral. All right, so that's going to be the integral from 1 to b. I'm going to bring that up and write that as x to the negative 2 dx. That's a basic power rule integral. So that's going to be x to the negative 1 over negative 1 by power rule. And then I'll clean that up a little bit, and then I'm going to write that as negative 1 over x, evaluated from 1 to b. And then let's go ahead and evaluate that and see what we get. So if we do this, we're going to have, first thing we're going to do is we're just going to do negative 1 over b. So see, now I'm doing the fundamental theorem of calculus, so I'm plugging that in. And then I'm doing minus, be careful, negative 1 over 1, like that. So that gives negative 1 over b plus 1, like that. So what I did is I changed that infinity to b, and then I just did an integral like you know how to do. Okay, is everybody with me on that okay? Okay. Now, what we do is we do something different now. We're not done with the problem. What we're going to do now is we're going to do this. We're going to do the limit as x approaches infinity of this answer. Okay, negative 1 over b plus 1 like that. Okay, so we can do that limit. And the reason we're doing that is because b is really going to infinity, right? So when we change that infinity to b, now if we take the limit as b goes to infinity, then we should get the value of that integral. Okay, so let's kind of think about what goes on in this. All you do on this, you did some of this in Calc 1, is when you did limits, if b is an infinite number, you just kind of plug it in like that. What happens if you do a number divided by something infinitely big? Where does that go? That goes to 0. If you don't remember that, that's a big deal. We're going to see that over and over again. So that goes to 0. And even if you have some number, I don't even care what the numerator is, if it's a constant, if you divide it by infinity, you're going to tend to 0. Even if that c is a trillion, it doesn't matter. Because infinity is infinitely bigger than a trillion, right? So it goes towards 0. So what that means is this is going to go to 0. You have 0 plus 1, like that. So the answer to this integral is 1. Okay? So we end up getting 0 plus 1, or that's equal to 1. All right, so we make this conclusion then. So what it is, we conclude that the integral from 1 to infinity of 1 over x squared dx is equal to 1. Okay, now that's pretty heavy for students a lot of times, is how could an area be just 1 if it goes on forever? Well, one thing that's happening though is x goes to infinity, it's just getting closer and closer to the x-axis. So it does approach a finite value. Now there's going to be times when you're going to see graphs that look a lot like that, but they don't converge to a point. So it's kind of weird. The mathematics, you have to kind of trust the mathematics sometimes more than you do your instincts by looking at that graph. Okay, do you guys got any questions about what I did there? That's improper integral number 1. And we're going to focus on that technique for a little bit and do these unbounded integrands. Okay, so here's on this next page what I had is I have a diagram. I just took this out of the book. And we're going to focus on improper integrals over infinite intervals. So when we're talking about an infinite interval, we're talking about the limits of integration have an infinity somewhere in it. And there's really 3 cases. So let's just kind of look over these 3 cases. Okay, the one I just did was something to infinity. So what this would mean is if you're doing an integral from a to infinity, what you do is you replace the infinity with a letter. I'm going to always use b just like the book does. and then you do the limit as b goes to infinity. So you change this integral from a to b, then you do the limit as b goes to infinity. So what this is saying is this is where the function starts. You're integrating that way, but then you're just making b go to infinity like that. So you change that integral into a limit. That's how you handle that, okay? Now, the second thing that could happen would be this, okay? You've got now you're negative infinity to b. b is a constant. That's fixed. So that part of the integral is fixed, but what's not fixed is the negative infinity. So what you do on this is you change this to another variable. So I'm going to use a. I just use a to b. That's the common way we do an integral anyway. So what I do now is I change that to the integral from a to b. Now notice I do the limit as a goes to negative infinity. So what this is saying now is we're going to go this way and do that limit as x goes to negative infinity. Does that make any sense? Is that logical? Okay, you're just using the idea of a limit. That's the idea. Now, the third case, and you got to be kind of careful about this one, if you're going from negative infinity to infinity, you have to break this up into two integrals, okay? You can't just go a to b. You can't do a limit approaching negative infinity and infinity at the same time. That doesn't make any sense. So what you have to do is you have to break it up like this. So notice what I do is I'm going to make that an a, then I'm going to make that thing a c. And then I have to do the limit as a goes to negative infinity. So I'm basically kind of c is some point in the middle here, and you're going out that way. So that's integral number one, okay? Then when you do the second one, notice what I'm going to do is I'm going to go from c to b, but I'm going to make the limit go to infinity. So I got to break this up into two integrals. This one's going to negative infinity, and then this one over here is approaching positive infinity. This one's going from c to b, this one's a to c. Okay, does that make any sense? Okay, well, we're going to do some examples of this, so I'll show you how you do that. You have to do negative infinity and infinity two integrals. You have to. Okay, it wouldn't make any sense any other way. Okay, another little bit of terminology is if you get a finite answer, like on the problem I did on the previous page, if you have a finite answer, then we say that that integral converges. We're going to use that terminology in Chapter 8 a lot. And then sometimes you're going to see that that area, when you do the limit can go to infinity. Sometimes you did that in Calc 1. Sometimes you do a limit and it goes to infinity. It doesn't have to go to some point. So this would be if there is an infinite answer. Okay? It doesn't converge to any point. Okay? So it's either going to be finite or it's going to be infinite. And if it's infinite, it's going to diverge. Okay? So that's the way that looks. Okay, so this is kind of important. This is saying that if you're doing a limit from negative infinity to infinity, you cannot do it this way. You have to break it up into two integrals. Okay, so that's the idea. So we're going to work a little bit. The first part of this section, we're just going to do some examples of each of those three cases and get you comfortable how those go. Okay? Okay, so let's go here and let's crunch some stuff out here. Okay, some of these problems I put graphs on your handouts, didn't I, on some of them? Yeah. Okay, you actually don't have to graph these things, but I find it very helpful to use your calculator so you can visually see kind of what's going on here. So this is an improper integral, and what it does is it has an unbounded interval, interval of integration. Okay? So what we do on this, we're kind of looking at really the cases on the previous page. So what you basically do with this, it's an improper integral, so you're going to change this into a limit. You're going to change that to some letter, let's use b. Okay, the zero's fixed. We don't want to mess with that. So what we're going to do is we're going to set this up like this. We're going to work with the integral from 0 to b of e to the negative 2x dx. And then what are you going to do? You're going to do the limit of what? B goes to infinity, right? Okay, that b is going to infinity. That's the whole key. You're setting it up that way like that. All right? Now, do you know how to do that integral? I hope so. Is that anything you need to do anything very heavy on, or is it just something you know? I hope you know it. Okay, there's a rule for that, right? Okay, the rule that we learned on that is the integral of e to the kx. That was what? 1 over k e to the kx plus c. Okay, so that's all we got to do on that then. Okay, so let's go ahead and work that out then. I'll keep kind of bringing the limit down. So we have the limit as b goes to infinity. And while I'm at it, let's see, that's going to be negative 1/2 e to the negative 2x. And then we're going to integrate from 0 to b like that then. Okay, we're going to go ahead and do the fundamental theorem. So next step, just keep bringing the limit down. So we have the limit, b goes to infinity. Now one thing you can do if you want to, see that's a constant. You can take that constant out. That's a limit law that you learned even way back in Calculus 1. You can take a constant out of a limit. So I'm going to write that as negative 1/2 times the limit like that. And then let's go ahead and evaluate this now. So I'm going to have e to the negative 2b, because I'm plugging the b in there. Then I'm going to plug the 0 in. So I'm going to have e to the negative 2b minus e to the negative 2 times 0 like that. Okay? Then when I do that, I'm going to have negative 1/2 multiplied by the limit. B goes to infinity. Let's just clean this up a little bit. I'm going to have you write this as 1 over e to the 2b. And then what's e to the 0 going to be? That's going to be 1, right? You can do that in your head. That's e to the 0, so it's 1. Okay? So is there any question about what I've done so far? Okay, now we're going to do the limit. Now you got to know the limit. The key thing that you want to look for is this kind of situation. C over infinity goes to 0. That's the key. So what you're doing with this, you don't have to necessarily write this step. I'm going to go ahead and write this because I just want to remind you of limit laws and how they work. So basically you're doing the limit of the first thing, then you're doing the limit of the second thing. And when you're doing your work, you don't have to write that step. You just need to understand that you can do that. So what you're doing is you got this. So this is negative 1/2. So what is this limit right here going to be? That goes to 0. The reason it does that is because that's 1 over e to the 2 times infinity. For all practical purposes, that's 1 over an infinitely big number. Agreed? If you take a number to the infinity power, you get an infinitely big number. So that is going to go to 0. So that means this is going to be 0. And what's the limit of 1 as that goes to infinity? That's 1. Okay, don't forget that. What is 1? 1 is a horizontal line. So and that's always constant. It's a horizontal line. So as you go to infinity, that thing's going to be 1, right? Okay. Okay, that's all Calc 1 stuff like that. Okay, so what we get is we have negative 1/2 times negative 1. So that gives 1/2. So that is the exact answer to that integral, and that would represent that area under the curve. And what we'd say on that is this converges. We just say that that's converging to 1/2. So what that means in my diagram on this graph is the area under this curve is finite, even though the graph goes infinitely to the right. Okay, it just gets closer and closer and closer to that x-axis, so it does converge to some value. To me, that's pretty interesting. What do you think? Just seems like it would be infinite, but it isn't. Okay, calculus kind of solves a lot of problems and paradoxes with infinity. That goes somewhere. That's where it's going, is to 1/2. Okay, any questions with that? Yes?
Do I have to create my limit?
Say that again?
Do I have to create my limit until the end? I mean, I know that I have to create it until the end, but like through the steps, are you gonna take
Well, yeah, there's different things you can do. I mean, you can do the integral at the side.
That's what
And get the integral done, then take the limit if you want to, like that.
Oh, just when you...
Yeah, you don't have to write everything the way I'm doing there. That's kind of a good way to do it, but as the problems get a little more complex, you'll probably see me just go over the side of the paper and just focus on the integral, then go back and do the limit. So that's fine, okay? Although sometimes if there's a tendency, sometimes students forget to do the limit. So, if you bring that limit down, it kind of reminds you, yeah, that's the last thing I do on the problem. Okay, but you don't have to. Okay, let's take a look at the next one here, and let's see what we got going on here. So again, this is an example of what you have is you have an infinite integral, or an infinite limits right there. So what we're going to do, anytime you have infinity in your limits of integration, you want to go ahead and change it to a limit. Okay, so we're going to change this to the integral from 4 over pi to b. You're changing that infinity to b. The integrand, which is what you're integrating, is 1 over x squared. Secant squared 1 over x times dx. And then you also got to do the limit as b approaches infinity like that. Okay, so that's what you're going to have. Okay? Okay, so now the focus becomes, let's focus on this integral. Okay, let me get my voice back. Okay, what do you think about a secant squared integral? What do you think about that? What if I just gave you, like on the gateway test, what if I was real nice to you and just gave you this one? What's that? It's tangent, right? Okay, right? So I'm thinking I've got a tangent integral here. It looks like U-substitution. Okay, so let's go ahead and play with this a little bit. U-substitution, we're going to do this. We're going to let that be the U. Okay, so we're going to have U is equal to 1 over x, or that would be x to the negative 1. Okay, we're hoping that dx would be this 1 over x squared thing. So du is going to be negative 1 x to the negative 2 dx, or du is going to be negative 1 over x squared dx, so we're only off by a constant, so we can handle that fine. So what I'm going to do is I'm just going to multiply both sides by negative 1, and you can do that in your head if you want to. You don't have to write that down. That's just negative du is equal to 1 over x squared times dx. Okay, so that means this piece right here, we're going to replace that with negative du, and then this piece goes along with that. So you have 1 over x squared dx is going to get replaced with negative du. Okay, while we're at it, we need to change the limits of integration, and then we're going to focus on getting our integral done then. Okay, so that looks like that's a nice U-substitution integral. Okay, now we're going to do the limits. So 4 over pi, you've got to change that limit of integration by applying the U-substitution. So what you're doing is you're doing 1 over 4 over pi, which just means a reciprocal. So that's pi over 4. Okay, that's all that's doing. And you're just doing 1 divided by 4 over pi, so it's 1 times pi over 4. Okay, the upper limit is b. You got to change that too. So you're doing 1 over b. So then that gives the limits of integration like that. Okay, so we got all the U-substitution going. Now I'm going to focus on the integral now, get that done, and then at the very end we'll do the limit. Okay, like that. Okay, so let's see kind of what we got going on here now. So let's go to the U-substitution. Okay, so I'm just going to focus on the limit. Okay, so we're going to have the limit from, or the integral from, that changed to pi over 4. The upper boundary went to 1 over b. Now our U-substitution, it looks like we're going to have secant squared of u, and then times negative du, so I'll put the negative there, and I have the du like that. Okay, so that would be the idea, and we can do that. That's a pretty easy integral to do. So if we do that, what's the value of that integral? Tangent, right? Okay, we know the derivative of a tangent is a secant squared, so that's going to be negative tangent of u, and then we're going to evaluate that from pi over 4 to 1 over b like that. Okay, I'm going to work that out. Okay, so let's see, I got a negative. Let's evaluate now. We have the tangent of 1 over b minus the tangent of pi over 4 like that. And let's kind of see what we got here now. Okay, there's one thing I know on this. Hopefully you guys know this immediately from trig. Pi over 4, the point on the unit circle is root 2 over root 2, like that. So what's the tangent of pi over 4? 1. That's important. Okay, remember tangent's y over x. So y over x is going to be 1, right? Okay, so let's write this as, and I'm going to distribute this negative through here. I'm going to go ahead and do that. So I have negative tangent of 1 over b, and then a minus minus is a plus. but we know that's equal to 1 like that. Okay? So that would be the value of that integral then. Okay, everybody okay so far? Okay. Right, now what's the last thing we do? Limit. Okay, we're now ready to do the limit as b goes to infinity, right? Okay, so what we want to do now at the very end is just do the limit as b goes to infinity of negative tangent of 1 over b plus 1. Okay, you can do that in your head. You got to think about this one though a little bit. So what we're going to do on this is let's just kind of think about if you replaced everything with infinity. So you would have like negative tangent of 1 over infinity. That just kind of helps you. And then that plus 1 comes down. Okay, well, what's 1 over infinity? Where's that going? 0. So what you really have is negative tangent of 0 plus 1 like that. Okay, so that means that if you look at a unit circle at 0 radians, you have the point 1, 0. So what's the tangent of 0 since it's y over x? That's 0, right? Okay, so that's 0. So what you would get then is negative 0 plus 1. So the answer to that improper integral is 1. Okay, so that does mean that converged to some specific point. Okay, and what that represents on this problem, we were doing the integral from 4 over pi to infinity. I don't remember on my graph how I did the window and everything, but if you kind of look at this, if you just said that this over here was 4 over pi, and I don't remember how I did that, then the idea would be that this area under this curve from 4 over pi to infinity would converge to some specific value. Okay? That's the idea. So what do you think? Okay, most of what you're doing is, if you think about it, it's skills you've already learned. You got all the integration skill, and you got the limit skill. Theoretically, those are things that in your past you can do well. So you're putting it all together, okay? All right, any questions on that example? Okay, so let's continue. There's a lot of different things that can happen on these, so we want to kind of get through lots of different examples here. So let's take a look at this next one. Again, you've got a infinite interval of integration. So you're going to approach it the same way. Okay, the first 3 problems are all approached the same way. So first thing you want to do is you want to change this to the limit as b goes to infinity. And again, you want to change that upper limit of integration to b. So we're going to go from 2, which is fixed, to b. Then we're going to do dy over y ln y like that. Okay, we're going to do that limit. Okay, so now the focus is the integral. What kind of integral does that look like? I think that's a good U-substitution one. Let's see. Let's think about that a little bit. What could I set u equal to? Yeah, ln y is a really good idea. Okay, all right. So we have u is equal to ln y. So that thing right there is going to be the u. Okay, now notice that du is what? 1 over y times dy, right? That is the rest of the integral right there. Well, you have dy over y. 1 over y dy is there. So that piece right there is just going to be du. So you have a real simple integral there. Okay? So now let's go ahead and let's work with the limits. I always got to change these limits too. So let's see. The b and the 2 would go like this. So what you're going to get on this, u is ln y. So you're going to get ln b is what that's going to go to. Okay, if you plug in a 2, you're going to have ln of 2 like that then. Okay, so now we're ready to do the U-substitution integral. Get that established, then we'll do the limit at the very end. All right, so let's see what we got going on here. Forget the limit for now. Let's just look at, we're going from, instead of 2 to b, we're going from ln of 2 to ln of b like that. Okay, now our integral's a real nice one. That looks like that is just du over u. Okay, so what's the value of that integral? 1 over u is what? Natural logarithm, right? Okay, so what you have is you have a natural logarithm of absolute value u, don't forget that, and then we're going to integrate from ln of 2 to ln of b like that. Okay, and we're going to plug it in, and we're going to get a mathematical expression that we can take a limit of. Okay, we get kind of a weird looking answer on this one. So we have ln of absolute value of ln b. Okay, that plugs in like that. You can do an ln of an ln. And then you're going to have minus the ln of 2. Okay, plug it in like that. That's the function that we're going to take the limit as b goes to infinity. Okay, it's okay. It can look weird like that. Okay, so now what we're going to do is this. We're going to do the limit as b goes to infinity of this expression, ln b minus ln 2 like that. Okay, now what I'm technically doing, you can always bypass this step, just be cautious about what you're doing, is you're doing the limit of each part separately. So I'm going to go ahead and just write that. That's a basic limit law that you know. So we're going to focus on doing those limits right there. Okay, all right, so let's see what happens. Well, what we're going to do is we're going to take that b, that's going to go to infinity. So let's just think about what happens. Let's just plug an infinity in there and think about what we have. We would have ln of infinity minus, and then this is a constant, right? So anytime you do a limit of a constant, what do you get? The constant, exactly. I mean, if you graphed the ln of ln2, it's a horizontal line. It's a constant. That's what it is. Okay, so that's just going to come down and be ln of ln2. That thing right there is a constant. Okay, so what you'd have with this one then is this. If you do a natural logarithm, and if you forget this, I mean, I'll just show you something on this. It's real simple. If you remember what the graph of a natural logarithm looks like, it's kind of like this. I'm just going to do this in a standard window just to remind you of something. Okay, here's the graph of a natural logarithm. Now, that thing is getting bigger forever, right? Okay, it never levels off perfectly. It gets bigger forever. So as b gets bigger, the ln gets bigger. So this whole thing right here is going to go to infinity. That whole thing right there. ln of infinity is infinity. And then if you take the ln of infinity again, you get infinity. So just think about that. That's really ln of infinity. This is still a constant like this. And then ln of infinity is infinity. Okay, does that make any sense? Okay, just the ln gets bigger and bigger and bigger and bigger forever. It never comes to an end. So here's what we get on this one. This one's kind of weird. All right, so we got infinity minus a number. For all practical purposes, that's infinity, right? Okay, because infinity is getting bigger and bigger. So what happened on this one is, when we did the improper integral, it went to infinity. It didn't give a finite answer. So what we say on this generally is we say that the improper integral diverges. Okay, now what that means is it means that that area, if you were looking at the value of this integral, and this is so weird to students, it's weird to me too, but the mathematics doesn't lie to you. It looks like on that problem, that's the graph. I don't think I put that on your handout. I don't remember if I did. But it would look like that would just have an area, wouldn't it? But it doesn't. Okay, it's infinite. That is very weird, isn't it? Because we've looked at problems that look just like that converged. So one of the things I say on this is, when you get into higher math, a lot of times you can't look at the picture all the time. The picture sometimes is deceiving. Okay, so that one diverges. Whereas some of the ones that are very similar, that converge to a value. That's weird, isn't it? Okay, that's how it works. So trust the mathematics. Okay, all right. You study a lot about this. If you're a math major, you study real analysis, and you study a lot about how these things like this work at a more theoretical level. So it's kind of interesting. Okay, so that one diverges. All right, everybody with me there? Okay, even though it doesn't look like it does, it does. Okay. All right, let's look at this example. We haven't done one like this yet. The only difference with this is this is negative infinity. So what you're looking at on this, you still change this to a limit, but you do it a little different. So you're going to set this up like this. We're going to write this as, first of all, you want to change your integral. You can use any letter you want there. You can use A or you can use B. I don't know. I think I'll just use B again. and then that's fixed as a 0. You just pick a letter, and then this is going to be the integral of dx over the third root of 2 minus x. And then you're going to do the limit now as b approaches what? Negative infinity. Now you're going to negative infinity. So it's just backwards of the examples we were doing. So your graph, you're just going from 0 to negative infinity. So on this graph right here, you're going that way now. So you're looking at to see if that region underneath the curve is going to have some answer. It's going to converge or diverge. That's what you're looking for. Okay? So we're going to focus now just basically on doing this integral. So this integral right here to me looks like, what do you think, U-substitution? Probably. Okay, it's probably a U-substitution integral. Okay, because we know how to integrate like something to the 1/3 power. That's the idea. So let's go ahead and get the U-substitution set up on this. So we're going to have U is equal to 2 minus x. That'll be the U part. Okay, du is going to be -1 times dx, like that. Well, let's divide by -1, and you're welcome to do that in your head if you want to. So that's negative du is equal to dx. So that means this piece of the problem right there is going to become negative du. Okay, like that. So we're going to have du over the cube root of u, which is something we can handle just fine. Okay, let's do the limits. And when I do the limits, let's see, we're going to go from b to 0. So you just do your u substitution. So we're going to do 2 minus b, so that would be the upper limit of integration. Then you're going to do 2 minus 0, and that would, hold on, I said that backwards. B would be the lower, and then 0 is the higher. So that's going to be 2 like that. Now we're ready to set up our integral. Okay. All right, let's set this up and let's see what we got now. So it looks like we got, we're integrating, the b became 2 minus b. Okay, the 0 became 2. So we've got that now. All right, and then we're going to integrate, it looks like we have a cube root of u, and then that's negative du, so I'm going to put the negative there and then the du like that. Okay, so that's what we're going to focus on integrating. Okay, so let's see, what do we have? We're going to write this as negative integral from 2 minus b to b, and let's write that, you can just do this all in your head, that's u to the 1/3, but then bring it to the top to be u to the negative 1/3 du like that. Okay, so everybody following along okay? Okay. Most of the work on these problems is integration, and most of the integrals are just going to be things you've learned in the past. Okay, so we got this. Now let's go ahead and integrate that now. So we have power rule. That would be u to the negative 1/3 plus 1 over the result. You're welcome to do that in your head if you want to. You've done that enough that you probably can by now. Okay, so that's going to be -3/2, because you're dividing, so you're multiplying by the reciprocal. And then that would be u to the 2/3, evaluated from 2 minus b to b like that then. Okay, so now we're ready to go ahead and evaluate that integral. And then at the very end, we'll take the limit, and then we'll see what happens on this one. Okay, so let's see what we got here.
Upper limit would have changed to b. B2.
What's that?
The upper limit. You've got b. It's going from b to.
Oh yeah, I did mess that up. Okay, I even have that over here. That goes to 2, right? Yeah, that, okay, now hold on, let's see. Yeah, the 0 went to 2, the b went to 2 minus b, right? So that means that we need to change those two things like that then. Yeah, okay. All right, thank you. Okay, so now we're solid. Okay, so now let's go ahead and let's do this. We have -3/2. Go ahead and evaluate. So that's going to be 2 to the 2/3 minus, and then this is going to be 2 minus b to the 2/3 like that. Okay, now you can leave it alone like that, or you can, you know, clean it up a little bit if you want to. It turns out that it doesn't really matter on this one. So I'm going to go ahead and just write this back like this. Let's just write this as the 3rd root of 2 to the 2nd And then let's write this as the third root of 2 minus b to the second, like that. Okay, so that's what we're going to take the limit of, and we're going to, as b goes to, this time we're going to go to negative infinity. Okay, so we want to go back to the original problem, and we were going to negative infinity now. Okay, so now let's do that. We're going to do the limit as b goes to negative infinity. That negative 3/2 can be written in front of the limit because it's a constant, so you can go ahead and do that. And then you're doing the limit of cube root of 4, like that. And then this is going to be the cube root of 2 minus b to the second, like that. So we're going to evaluate that limit and see what happens. With a little practice, you get to a point where a lot of times at the end, you can just kind of do that in your head. Okay? So what I'm going to do is I'm going to write this as negative 3/2, and then you're going to do the limit as b goes to negative infinity of that constant. We know what that is. Then we're going to do the limit b goes to negative infinity of this cube root. So that's what we got to focus on. Okay. All right, so what we have is we have negative 3/2. What's the limit of that constant? That's just that constant. Okay, so we got that. Now think about this one for a little bit. Just think about if b goes to infinity, what you would have is you would have the cube root of 2 minus infinity to the second. For all practical purposes, that is the cube root of infinity, right? Okay, you can just ignore the 2. That doesn't really make any difference. If you square that, you get infinity squared. Okay, yes?
Does it matter if it's positive or negative? It's minus negative infinity.
That might, okay, yeah, on this one it won't make any difference because you would really have kind of, you can think of this as 2 minus negative infinity, right?
It would still work out.
And then it's still, for all practical purposes, it's infinity anyway. Okay? All right? Yeah, even if it turned out to be a cube root of negative infinity, that's still infinity. That's okay like that. So the thing is on this, you're just doing the cube root of an infinitely big number, so that goes to infinity. Okay? When you do a cube root, it gets bigger and bigger and bigger forever. If you did a cube root of 1,000,000, and then you did a cube root of 1,000,000,000, the cube root of 1,000,000,000 is a lot bigger. It gets bigger forever. So that means this thing is going to infinity, so we got that. So do we have a finite answer or do we have an infinite answer? That's infinite, isn't it? You got an infinity in there. Okay, for all practical purposes, that thing right there is infinite, right? Okay, so what if it's negative infinity? It doesn't make any difference. This whole thing right here is going to infinity. Okay, it's really going to negative infinity because that thing right there is negative. Well, actually, then if you had a negative times a negative, that'd be a positive, but it doesn't matter. Okay, so the thing is, this would be another example of one that diverges. Okay, so that region, even though if you look at it graphically, you might think that it might converge to a value, it does not. The math doesn't lie. So that one does not converge to any finite value. Okay, and what you're doing geometrically on this is you're looking at the area under the curve from 0 to negative infinity. Okay? So you guys with me how you know something diverges? The answer goes to infinity. That doesn't converge to any finite value. That's it. And that'll happen sometimes on the problem. Don't let the graph mislead you. Trust the integration techniques and the limit techniques that you've learned. Okay? Okay, so let's see. Let's move on to this situation. I'm going to do this one. Then example 6 is a little different. We hadn't done that type yet. And we'll focus on this a little bit. Okay, so what we have here is, again, you got the same thing. You got 0 to infinity. We're just focusing right now on the limits of integration have an infinity somewhere in it. So what you do in this case, you always set it up the same way. You change that integral from 0 to b. And you know what I've got is, here's what I'm going to do on this problem. I have a u. I'm going to do a u substitution. So I'm going to change this. You're allowed to do this. I'm just going to change the problem to e to the x over e to the 2x plus 1 dx. You're allowed to do that. The reason I'm doing that is because I know I have to do a u substitution anyway, and I don't want to do u when I already have a u. Does that make any sense? Okay, I mean, you don't have to do it. You could also do a v substitution, or just pick any number you want to do. So I'm going to go ahead and do that, and then what we'd do is we'd do the limit as b goes to infinity like that. Okay, so let's just use x instead. Okay, this is actually a very good U-substitution problem. And the way to look at that is I'm also going to maybe change this and rewrite it this way, because you'll probably see this better. I'm going to write that as e to the x to the second. Okay, that's what e to the 2x is it's e to the second to the e to the x to the second. All right, does that make sense? Okay, so you multiply the exponents. You'll see the U substitution better if you look at it that way. Okay, so what I'm going to do on this one now is we're going to let u be e to the x. Okay, now what's going to happen on this one? See, that'll just become u. That'll become u to the second. And then the denominator is u to the second plus 1. So tell me if you know how to integrate something when it's the denominator is u to the second plus 1. Do you know that? That's arctangent, right? Okay, that's what that is, okay? Now, du is going to be, well, we know the derivative of e to the x is e to the x dx. So that means that this thing right here, that can be your du. Okay, like that. So we're going to replace this with du while we have u just being e to the x like that. Okay? Now, you also want to change the limits of integration as you're doing this too. So let's go ahead and get the limits taken care of. Okay? So when we do this then, since we're doing a u substitution, let's see, the b is going to become e to the b, and then the 0 is going to become e to the 0. So that's going to go to 1. So I'm going to integrate from 1 to e to the b. Okay, like that. Everybody with me okay? Okay, so let's go ahead and let's do the integral and let's kind of see what we got going on here now. So let's see. We're going to ignore the limit. What I'm going to do is we're going to have the integral from the 0 became 1. And then the b turned into the e to the b. Okay, we have du over u to the second plus 1 like that, okay? And what you learned is this is basically just an arctangent. So even back in Calc 1, you learned that if you do the derivative of an arctangent or an inverse tangent, depending on how you want to write that, that derivative rule is 1 over 1 plus x squared. Okay, so that means that integral is just an arctangent. Okay, so that means that what we would have is I'm going to write that as inverse tangent of u. Then we're going to evaluate that from 1 to e to the b like that. Okay, so that's a derivative rule. That's why I did the u substitution that I did. Then what I'm going to have is when I evaluate this, I'm going to have the inverse tangent of e to the b minus the inverse tangent of 1 like that then. Okay, and then we're going to kind of look at thinking about that a little bit. You got to know a little bit of trig there to get this worked out. Okay, so in trig, one of the things that shows up is when you're doing an inverse tangent of some number like that, there's a couple of things that are important. First of all, the range, and this is something that just shows up every now and then. You want to remember it. You guys remember what that is? Negative pi over 2 to pi over 2. We've actually seen that a couple of times this semester. So when you're doing an inverse tangent, you want to make sure that your answer falls within the boundaries negative pi over 2 to pi over 2 in radians. And then what happens on this one is, if you know your unit circle good, you could tell me what the inverse tangent of 1 is. Can you do that? Pi over 4. Right, okay. Because what happens is, at this point on the unit circle, that's the easiest one to remember. That's the angle pi over 4. And y over x is 1, right? Okay, so that thing right there is pi over 4, and pi over 4 does fit in that range. So what you're going to have is you're going to have the inverse tangent of e to the b minus pi over 4 like that. Okay, so that's the idea. Okay, so that's the integral. Now we got to do the limit. Is everybody okay on that trig? Because that's going to show up from time to time. Okay, so now what we're going to do is we're going to now we're ready to do the limit as b goes to infinity of the inverse tangent of e to the b minus pi over 4. Okay, now, I'm going to skip the step where I'm showing that I'm doing the limit of each part. You're welcome to do that. So what we're doing is, when we're doing this, we're doing the inverse tangent of e to some infinite number. And then we know the limit of pi over 4 as b goes to infinity is just that constant, right? So we got that. Okay, for all practical purposes, we are doing the inverse tangent of an infinite number. That's what we're doing. Okay, now your ability to do this, again, depends on your trig background a little bit. So a couple of ways that I can explain this is like this. Okay, one way to explain this would be to just remind you of how a graph of a tangent goes. Now, if you do that, that'll help you a little bit. Okay, so one thing that happens on a graph of a tangent is, on a unit circle, when you're at pi over 2, what is the value of the tangent at pi over 2, since it's y over x? It's undefined, right? So what you learned in trig is that would be a vertical asymptote right there, okay? The other thing that happens is at negative pi over 2, what's the tangent of negative pi over 2? It's undefined because it's y over x, right? Everybody with me on that? Remember that? Okay. And then the other thing that's kind of helpful to know is halfway in the middle, if you do a graph of a tangent, it roughly looks like this. We don't have to have all the details ironed out. We just got to have that. Okay, so what we're doing on this then is we're doing an inverse tangent of an infinitely big number. So think of it this way. All right, where does infinity fall on this graph? It's real close to pi over 2, right? So right there, that thing's going to infinity. So if you're doing the inverse tangent of infinity, aren't you heading towards pi over 2? And so remember, when you do an inverse trig function, you're giving me an angle, right? So as you get close to pi over 2, that graph is going to infinity. So the value of this is going to end up being pi over 4. Okay, that's what that's going to be, if you look at that the right way. Okay?
Is it because it's undefined infinity, tangent inverse?
What's that? Or not pi over 4, pi over 2. What'd you say?
Oh, so you said the tangent inverse of infinity is going to be pi over 2?
Pi over 2, yes. Okay, yeah, because what's it doing? What is the tangent real close to pi over 2? It's going to infinity, right? Okay, and remember, the range of an inverse tangent is this. You can only give me an answer from negative pi over 2 to pi over 2. Now, you can go ahead and give pi over 2, because when the tangent's infinite, you're getting very, very close to pi over 2 like that. So what you would do then is you would conclude that that's pi over 2 minus pi over 4, like that, okay? And then when you do that, you get a common denominator. That's pi over 2 minus 2 pi over 4, okay, like that. Whoops, why am I doing that? I'm doing that backwards. Okay, need to do it like this. So this would be 2 pi over 4 minus pi over 4, so that means the answer is pi over 4. Okay, so that area that we're looking at is going to converge to pi over 4. Okay, and if it converges, you don't have to write that it converges, but I just want to kind of get you familiar with that for when we get to series. Okay, so actually what this means, I don't remember if I put a graph on yours or not, but I went ahead and graphed this on the calculator, and if you're integrating from 0 to infinity, you get a region that's going to converge to pi over 4. Okay, the part of this problem a lot of times that students do not get is the trig background stuff. So the key thing is this right here. Does that make sense? Okay, when you're infinite, that's where you're close to. Okay, that's the idea. All right. So that, and the other thing is, like, what if you had inverse tangent of negative infinity? And what would that would be negative pi over 2, right? It wouldn't go outside of that because of this range. Okay, whenever you're doing an inverse tangent, you got to focus on that part of the graph only. That's it. Okay, so that would be the idea. So that one converged. Okay. Okay, any questions on that? Okay, we hadn't done one like example 6 yet. This is totally different. This has got a little bit more work involved in it. So when we do this improper integral, Let's see. Well, let's go ahead and take a break here, okay? This one will take too long. Okay, this one takes a little bit of work. So let's go ahead and do our break now. See, this one. What's different on this one is negative infinity to infinity. Okay, now what I said you have to do on this is you have to break this up into two integrals. Okay, you have to do that in a certain way. Now, I got a graph here. I don't remember if I put a graph on your handout or not, but what happens on this one is you're looking at the area, you're trying to see if that area converges to some precise answer from negative infinity to infinity. So what you want to do is you want to break it up into two integrals, okay? And it goes like this. First integral, we're going to go from negative infinity, and you're going to pick some value there. Now, the best value to choose generally is 0, because I like calculating with 0, and you do too, right? So we're going to use 0. So we're going to do that limit like that. And I'm just going to leave that alone like that. And then we're going to do the second integral. We're going to go from 0 to infinity of the same thing. Okay, like that. So that's how we're going to kind of think through that is like that a little bit. Then we will do the limits. Now I also want to do the kind of set up the limit idea on this before I actually focus on the integration of this. So what you're doing with that then is you're doing this. You're going to write this. You're going to do the limit of each integral. So this one you're going to change this to pick a letter. Like let's call that maybe like A or something. Okay. So I'm going to call that A to 0. I'm going to do that like that. And then I'm going to do dx. Then I'm going to do x squared plus 2x plus 5 like that. We'll work on that integral. And then what we're going to do there is you're going to take A is going to approach negative infinity, like that. So we're going to make that approach negative infinity. See, we know how to do that integral. That's an improper integral that we've been working on, that type. Okay. Then what we're going to do is we're going to do the second one. Okay. You're going to change, just use the same letter. Okay. That's going to be A again. So I'm going to say A to infinity. Like that. Whoops, I'm doing that wrong. I'm not paying attention here. That's got to stay 0. Okay, it's this one that changes. You want that one to go to a different letter. Okay, so we're going to take that to like something like B. And then we're going to have dx over x squared plus 2x plus 5. And then that limit is going to, B is going to approach infinity. So let me pause there and kind of explain what I'm trying to do here. Okay. So the idea is I picked 0 just because the function's continuous. That's the first thing that's important. It's continuous everywhere. I like 0 because it's easy to calculate with. Okay, you agree? That's why I did that. So again, what I'm doing is I'm integrating 0 out to negative infinity. So I'm going from negative infinity to 0. Then I'm going from 0 to infinity. So again, I'm doing the limit as b goes to infinity. And I'm doing the limit as a goes to negative infinity. Okay, how's that look? Okay, not bad. Okay, all right. So now what we have is we have two integrals, the same kind of thing we've been working on. So we just need to work on the indefinite integral first of all. Let's just kind of do that and think about what kind of integral we have here. Okay, so let's look at doing just both of these integrals kind of separately like this then, okay? What kind of integral do you suspect this is? We've done that before. Completing the square, exactly. Okay, it looks like one of those completing the square things. It's not partial fractions. You know why it's not partial fractions? Because it doesn't factor. Okay, it's prime. Okay, if it factored, then yeah, we'd factor it and then we'd go to partial fractions. So what we're going to do on this is complete the square. I'm just going to kind of do this over at the side here. So we got x squared plus 2x plus 5. Okay, so we're going to do this. Going to take half of the 2, so 2 over 2 is 1, and you're going to square the 1. So you're going to add 1 here, and then you're going to subtract 1 there, and you're going to have a perfect square there just for simplicity. This one's going to factor as x plus 1 times x plus 1, and then this is going to be plus 4, so that gives x plus 1 to the second plus 4 like that. Okay, so that's going to be the idea is we're going to get that set up like that then. Okay, so I'm going to go ahead and just forget about the limit. I'm just going to save a little bit of work. I'm just going to write this as a to 0 dx over x plus 1 to the second plus 4. Okay, and when I go over here, I'm doing the same thing. You're going to get the same integral, except the limits of integration are different. So we're going to have dx over x plus 1 to the second plus 4 like that. Okay, now you got a formula. So the formula that we learned goes like this, and I'll write the formula over here. So we learned the integral of dx over x squared plus a squared. That's the one that went like this: 1 over a inverse tangent x over a plus c. Okay, so that's what we learned. That's what that's going to. That has that same kind of structure like that, right? Okay. Now you can do a U-substitution, but you can generally process something at this level in your head. I'm going to go ahead and just kind of show you the U-substitution. So if you let u be equal to this thing, x plus 1, okay, then what you would end up having is you would have du is just equal to dx. So really all you're going to do on this, now you can go through the details of U-substitution if you want to, but really what you're going to have is this. Okay, you're just going to have this, use this same integral formula, but instead of having an x, you're going to have an x plus 1. Okay, so I'm just going to go ahead and not go through all the U-substitution process because you don't have to do it on this problem necessarily. And I'm just going to write this. The value of this integral turns out to be this. Okay, so first of all, in this problem, what's a? A is 2, because that's what's being squared, right? So a is 2, like that. Okay, so when you do this integral, what you're going to have 1 over a, which is 2. Then you're going to have the inverse tangent of, instead of x over a, you're just going to have x plus 1 over 2. If you did the details of U-substitution, that's what you would get. A lot of times if your x is just off just by a plus or minus, then you can just do it that way. Okay, but you do what you need to do. And then this thing is going to be evaluated from a to 0, like this. And then over here, same thing. The value of this integral is exactly the same thing. The antiderivative is 1/2 inverse tangent x plus 1 over 2. And we're going to evaluate this one this time from 0 to b. Okay? All right. Any questions so far? Okay. So now what we need to do is we need to crunch all this out. And this one's going to take a little bit of work. So first of all, when we're doing this one, and then we're going to do the limit, I'm just going to write this as 1/2. Then I'm going to plug in the limit. So I'm going to have inverse tangent. Do some stuff in your head on this. If you plug in a 0, you have inverse tangent of 1/2, and then minus inverse tangent of a plus 1 over 2. Okay, like that. Okay, and then I'll take care of that, and we'll end up doing a limit on that in a little bit here. Okay, then we go over to this next one. It's going to be 1/2. Okay, similar idea. You're going to have inverse tangent. If you plug the b in, you're going to have b plus 1 over 2 minus, and then you're going to have inverse tangent of 1 over 2. Okay, plug in the 0 in, you have 0 plus 1 over 2, so that's 1/2 like that. Okay, now when we do this, we're now pretty well ready to go through and start thinking about the limit and kind of seeing what we have here. So let's now think about just doing the limit. Okay, so when I do this, let me move this around here a little bit. Okay, and we'll just do all this kind of in our head. So we're going to bring the half out, and we're going to do the limit. Now this time we're doing a approaches negative infinity. So if you kind of go back up to that original integral, that was going to negative infinity. So we're going to take a to negative infinity of this stuff right here. We'll have inverse tangent of 1/2, and then we'll have minus inverse tangent of a plus 1 over 2, like that. Okay, then we can process that mostly in our head. Okay, then we're going to move over here and do this. So we're going to have 1/2, and we're adding these two things together. I'm going to go ahead and put a plus there now because we're adding the results of these together as we're doing the limit. Okay, so I'm going to have now 1/2 times the limit. Okay, where does b go? B goes to infinity. Okay, so we're going to have the limit as b goes to infinity of inverse tangent b plus 1 over 2 minus inverse tangent of 1/2 like that. Okay, so now we're ready to do the limit. Okay, everything solid? Okay, I got it. Like I said, most of these integrals are things you've seen in the past. So the big work of the problem is the integration, then you finish up with the limit. Okay, so if we did this, we would have 1/2. Now see, the limit of the inverse tangent of 1/2, that's a constant, right? So what's the limit of inverse tangent of 1/2? It's just that itself, right? That's a constant. Okay, that's not a variable expression, so that is the value of that limit. Okay, this right here, for all practical purposes, if you let that a go to negative infinity, you're going to end up kind of having this, okay? Negative infinity, just think of this as negative infinity, right? You don't have to write all that down. You don't have to write down negative infinity plus 1 over 2. For all practical purposes, isn't that just negative infinity? Now, negative infinity is important because of the way that works on an inverse tangent. Okay, so we got that. Now we go to the right side, we would have 1/2 times the limit as b goes to infinity. Okay, now if we let b go to infinity, that really just means inverse tangent of infinity, right? Infinity plus 1 over 2 for all practical purposes is infinity, right? If you take an infinitely big number, add 1 and divide by 2, it's still infinite, okay? And then this one would be minus the inverse tangent of 1/2. That's a constant, so that's the value of that limit. I do not need that limit there, though. I just took the limit, so I don't need that. Okay, I don't know why I wrote that. Okay, so that's our limit. So now what we're going to do is just kind of put this together and kind of see where this leads us then. Okay, is anybody's having any trouble following so far?
What was that first one, negative infinity?
Okay. Yeah, you can kind of do a little scratch work on the side, right? You're talking about this one right here?
Yeah.
Okay, because I'm letting the limit go to negative infinity.
Oh, okay.
So see, I just got negative infinity plus 1 over 2. That's negative infinity. And if you divide it by 2, it's still negative infinity. Right? And that's important on an inverse tangent because of how the asymptotes get. And we saw that in a previous example. Okay? So anyway, what we have here now is we got this. Okay, so this would be 1/2. Okay, and I'm going to go ahead and just distribute this out now. That 1/2 out, so that's 1/2 inverse tangent of 1/2 minus 1/2. Now you got to reason out what this is. Okay, now that thing we saw in a graph earlier, so let me just re-sketch this graph at the side. You don't need to write this down. But when this shows up, you want to remember that the inverse tangent is defined from negative pi over 2 to pi over 2, and that basic graph that we did looked like that. Okay, so what would be the value when the function's negative infinity? What are you getting close to? Negative pi over 2, right? So this thing right here is going to be negative pi over 2. Okay, that's how that works out. We saw that in the previous example, so that becomes negative pi over 2 like that. Okay, then what we're going to have is that'll take care of that piece right there. Now we just move over to this right side, so we're going to have 1/2. Okay, and let's see if we got this down. Okay, if the inverse tangent is infinitely big, okay, if the function's infinitely big, where are you? Pi over 2. So that thing right there becomes pi over 2. Okay, that thing right there, I'm going to distribute. Oh, I need to take that 1/2 like that. I'm trying to distribute the 1/2 as I go. So I have 1/2. That thing right there goes to pi over 2. Okay, and that's kind of the critical part of the problem. And then we're going to have minus 1/2 inverse tangent of 1/2 like that. Okay, so now we're getting close to having this done. All right, what do you see happening here? We've got a cancellation, don't we? Right, see this? So that cancels out. That and that's gone. So now we just have the arithmetic problem. This would be pi over 4. If you do that, this would also be pi over 4. So that means the answer is 2 pi over 4, which reduces to pi over 2. So that one does converge. Okay, that's a really kind of cool problem. Okay, what's up? I forgot what? No, I think I'm okay. All right, yeah, the negatives, I think you had a negative times negative was a positive, wasn't it, right there? So that's why that one became positive, so I gave that. So that's how you handle the improper integral when it's from negative infinity to infinity. And what that would be saying is, this is what the graph of that looks like. So to me, that's very fascinating. I don't know about you, but that whole area right there is approaching that finite value. Okay, like that. Okay? That almost looks like a bell-shaped curve that you would do in statistics. It's not, but it resembles that. Okay? And a bell-shaped curve, if you ever study statistics, a bell-shaped curve like that, you know what the area under that is? 1. And that represents the total 100% probability. So if you ever study statistics, you'll learn about the bell-shaped curve, and that's represented by a function, and that area converges to 1. It's kind of interesting. That's 100% probability. Okay?
So for these questions that are the integral from infinity to negative infinity, we just chose 0 as our c. Are there going to be any problems that lend themselves to a value for c being something different than 0?
Yes, and we'll get to that in a little bit here. Like, for instance, if you had an asymptote at 0, you know, it would be a totally different kind of approach. So the reason I did that, in general, if it's a continuous function, and it has to be a continuous function, that's a part of the definition, just use 0. Okay, because it would still work out if you used anything else, but it's simpler generally to use 0 because of the computation. Okay, like that. So yeah, if you had an asymptote at 0, the graph was undefined there, you couldn't even do it this way anyway. Because if you go back and look at earlier in the notes, when we like these 3 cases are on page 2 of your notes, notice that it says if f is continuous, if f is continuous. So if it's not continuous, then it's a totally different approach. Okay, so that's what you're asking. That's a good question.
So,
yeah.
In the case if we had like a U sub, would that 0 mess up anything? Or?
Say that again.
If we had like a U sub situation,
right?
At 0, mess anything up when we change the limits? Yeah,
the reason I didn't change the limits on the one I just did is because I could process that integral in my head. That's the reason I didn't do that. I could have done that last one by U-substitution also, but it only had an x plus 1, so I could process. That's why I didn't change the limits.
But in case we did have to.
Yes, if it's a U-substitution, change the limits, absolutely. Okay, and we've done that if you've kind of followed along on, like this previous example, we started from 0 to b, we ended up 1 to e to the b. So we changed the limits. So yes, you want to do that. Okay? All right, you good? Okay. All right, now we're going to transition now to the next kind of thing that happens. And there's kind of 2 main areas of improper integrals. That's the first type, where the limits of integration have infinity in it. That's type 1. The second type is something like this. Okay, if you were looking at, for instance, the graph of 1 over the square root of x. Okay, and if you were going to do a integral, say you were going to do an integral from 0 to 1 on here. Okay, if you were going to do this integral right here, okay, well what's different is the limits of integration are finite. There's no infinity there. But what's different about this one is what's happening when you're at 0. As you're going to 0, what's happening to the graph? It's going to infinity. Okay, so what we have is this thing is unbounded. Okay, that's the other case, whereas these things are bounded. So you have bounded limits of integration, but you have an unbounded region you're looking at. So the idea on this is you have a vertical asymptote, essentially. So what we're going to look at in these cases mostly is how do you handle it when you have a vertical asymptote at where one of the limits of integration is really approaching infinity, you have a vertical asymptote. So that's the idea. So here's what we do on this one is we kind of set this one up kind of like this. Well, what we have to do is we change this thing. We have a problem area at 0. That's where the asymptote is. Wherever the vertical asymptote is, that needs to be like, pick a variable there. So change that to a variable. You can leave this alone because that's finite, and there's no problem at 1. There's no asymptote there, so you do that. Then you go ahead and do the integral, 1 over x dx like that. But then what you do is you do the limit, but you're going to do a right-hand limit, like this. You would say as x approaches a from the right-hand side. That would be how you set that one up basically. So the idea is, and you'll see this kind of case right here, you got an asymptote, that's the key. The reason I'm going from the right-hand side is because I'm looking at this is finite and bounded, you're going that way. You're heading towards that asymptote from the right. Okay? If you were doing an integral in this area, then you would do a left-hand integral. Okay, does that make sense? Left-hand limit. Okay? So that's how you're going to set that up, is you got to change, this is wherever the problem area is. The one that's got the vertical asymptote is what you're going to use the letter on. And then you got to figure out how to do that limit. Okay, so that's the idea. Okay, does that make any sense? I mean, just to start. Okay, all right. So let's go to the next page. I'm not going to really do that problem. That's just something I took out of the book, and I thought that had kind of a nice diagram to it. Okay, so let's look at these 3 situations. These are the key situations that you're going to encounter. The key thing is, on this integral right here, these are bounded. A to B, the limits are bounded. Okay, what's unbounded is the integrand. This region right here is unbounded. Okay, you have an asymptote right there. So you probably have a vertical asymptote at A. Okay, because it's going to infinity. That's how it behaves around a vertical asymptote. So the way that you would do this then is, again, the problem area is the one that's going to get changed. Okay, so you have a problem area at A. So that A, you want to pick a new variable. Okay, B is okay, so you just leave that alone. And then what you're going to do on this one is you're going to do a right-hand limit towards that asymptote. So that's what that right there means, is you're doing a right-hand limit. So change that and then do a right-hand limit. Okay, does everybody understand that? Why right hand? Well, because the region's all to the right of the asymptote. That's why. Okay? Okay, look at this situation. Opposite situation. Okay, you're looking at the region from A to B. Okay, again, you have bounded limits of integration. That's not the problem. Okay, but you have a problem there. So you have a vertical asymptote there. So this time what we do is that thing gets changed to a generic variable, whereas this thing stays fixed. On my graph, there's nothing going on at A. It's just no asymptote or anything. Then what you're going to do on this one is you're going to do a left-hand limit, and that's because the region you're integrating is to the left of that asymptote. Okay, so you're going to do a left-hand limit as you approach that value like that, as you approach the problem area. All right, is that logical or illogical? Okay, all right. Okay, now here's the next thing. Okay, well, what we have on this now is the vertical asymptote is in the middle. Okay, if it's in the middle, you got to do 2 integrals. So the idea is going to be your problem area on here is you have a vertical asymptote somewhere in the middle of your region. So what you have to have is you got to have 2 integrals. So when you do this integral, what you're going to do is you're going to integrate from A to some letter. Okay, you can use whatever letter you want here. You could do like, what did they use? They did C, okay, like that. And then what you're going to do is you're going to do the limit as C as basically that approaches some value like this. Actually, they used a P, didn't they? They did that, okay? So they're saying C approaches P from the left-hand side. So you're doing a left-hand limit right there, okay? So just look at that. That's a left-hand limit. The reason is because the area, the region is to the left of the asymptote. Okay, then when you do this one, what you're going to do is you're going to do the integral from, like they've done here, you got a different value, d to b or something like that. And what you're doing now is you're doing a right-hand limit. Okay, so you're going to take that d as it approaches p from the right-hand side like that. So the idea with this one is, it's just like combining the last two things and splitting it up into two integrals. So that right there is a left-hand integral. Does that make sense? Why? Okay, because you got an asymptote. You're going from there to there. And then right-hand limit here, you're approaching that asymptote from the right. So the asymptote is the problem area. Does that make sense? Okay. Yeah? No? Okay. All right, so let's see what we got going on here. So we want to try to get some of these things set up. Okay, so we're going to look at kind of the different situations on here for a few minutes. And let's see what we got. Okay, now I think it's pretty helpful on these things to graph visually to see what's going on in the problem. But the first thing you want to look at on this is, and you don't have to graph actually, the idea is on this one, you would know where the vertical asymptote is on this problem without looking at the graph. Where's this thing undefined? 0. Okay, so you have a vertical asymptote at x equals 0. You can't have 0 in the denominator, so we know that. Okay, so that's where our problem area is. So what we're going to do, I went ahead and did a graph on this on the graphing calculator. So that's 8 out there, there's 0 there. So you're going to be integrating in that region right here. So you're actually looking at that shaded region right there below the curve. Okay, but that's unbounded because of that vertical asymptote like this. So here's what you want to do when you set this up. Okay, which limit gets changed, the 0 or the 8? Where's the problem area, 0 or 8? Okay, whatever the problem area is, you want to change that variable. And who cares what you use? It doesn't matter. Let's just say b. That's what you use most of the time. And then that's going to be okay. See, that's okay. That's the vertical asymptote. Okay, so you're going to do that. Now, we don't do anything with this limit. Now, you could go ahead and write this as x to the 1/3 dx. You might as well do that because you're going to have to integrate it anyway, and that's a power rule, right? Okay. Now what you got to do is figure out which kind of limit we have. So b is going to approach from which side? It's going to go this way. You go towards the asymptote from the right, so you're going to approach 0 from the right-hand side like that. What's that? Right here? No, this is a right-hand limit. Yeah, because we're coming from the right.
But your x is in the denominator.
Oh, that thing. Yes. Okay, sorry. Okay, yeah, that's -1 there. I'm trying to do too much in my head. Bring it to the top, change it like that. Very good. Okay, so now we're all set up. So does everybody understand why I set that up the way I did? Okay, the region's on the right side of the asymptote, so do a right-hand limit. That's how you know that. Okay. So now this is a pretty easy integral to do. So what we're going to do is we're just going to go ahead and integrate that. That's with the power rule. That's going to be limit b goes to 0 from the right-hand side. If you do a power rule on this, you're going to have x to the, let's see, add 3 halves. That's going to be x to the 2/3, like that. And then over 2/3, evaluated from b to 8. Okay, so that's going to be, that's a 3 halves. So I'm going to go ahead and just take that 3 halves out of the limit. So we're going to do the right-hand limit. And then we're doing the 8 to the 2/3, or x to the 2/3, evaluated from b to 8 like that. Okay? I can skip a couple of steps because now what we need to do is just do 3 halves. We're going to do the limit as b goes to 0. And now if you plug in the limits of integration, you're going to have 8 to the 2/3 minus b to the 2/3. Okay, like that. And then we can go through and kind of see what happens on that. Okay, well, first of all, if you have 8 to the 2/3, that's just a constant. and that's really the cube root of 8 to the second. One way to write that's like that, okay? And then the cube root of 8 is 2, so 2 to the second is going to be 4. So that's what that's going to be. So what you would end up having then is when you do this limit, what you're doing is that's a constant right there. So that's just a 4. You're doing a limit. You don't have to break it up into 2 limits. You can if you want to, but you can just do that in your head. Now this thing right here, we're just going to plug in a 0. Okay, we're coming from the right-hand side. The idea would be if b was slightly bigger than 0, you would approach some value. So what we do now is we just do 0 to the 2/3, plug it in, 0 to any power 0, so that would be 3/4 times 4, okay, like that, okay. Then, let's see, then I would end up having 4.
3 halves.
Did I miss something on that? Oh, 3/2. I love the stupid things I'm doing today. God. Just dumb things. You guys ever do stuff like that? Like when you're doing homework? Doesn't that just drive you crazy? I don't know why. Just as you do that. I think sometimes you get tired and you can't see what you're doing and everything too. So that's 12/2, so that's 6. Okay, like that. Okay. So that's the idea with that problem is you set up the limit. The key is setting up the limit on the improper integral, but the integration wasn't very difficult, was it? Okay, so it's the setup you got to focus on. All right? Yeah.
Can you just remind me of the difference between left and right hand limits?
Okay, yeah. Okay, the thing is, if your asymptote, notice on this that your region is to the right of the asymptote. That's why you're closing in from the right-hand side.
But you still just substitute the number in?
Yes. Yeah, and it won't really matter. Like when you were in Calc 1, like if you plugged in like 0.0001, you still go to 0. Okay? The idea when you're doing the limit as x goes to 0 from the right-hand side is it's where it's going. Okay? So the closer that gets to 0, the closer that just becomes to 0 to the 2/3.
Wouldn't it like be the same if you in the left?
Yes.
Or, oh, it's just different if you.
Yes.
Because they're going in different.
Right. So the thing about that is you know, you're just taking a number very, very close to 0 from the right-hand side. It's going to be 0.
It would be different. Okay.
Yeah, exactly. Yeah, okay. Yeah, if you did like even if you did like a left-hand limit on there, you still think of it the same way.
In this case, it would be the same, but there's
Yes.
other cases where you could have different.
Right. So like if you were doing the left-hand limit around 0, it would be negative 0.000 something, like that. So you can think of it that way. Okay, so that one diverged, okay? So that region from there to there, even though it has that asymptote, does diverge to, or converge to 6, okay? Which is kind of interesting, okay? All right, let's look at the next one. Okay, what do you think of a secant tangent integral? What if that was on the gateway test? Would you like that? Yeah, because what do you differentiate that gives you a secant tangent? A secant, okay, I like that integral, okay? Sometimes they're real simple. Okay, so what we're going to do on this one now is you got to know where the asymptote is on this one now. So a couple of things that you could do on this one. I'm trying to have you think through this without graphing so much, but I do recommend you do these on the graphing calculator so that you get a clear picture. But the idea with this one is if you're at pi/2, if you were to do the secant of pi/2, can you tell me what that would be? What is the secant? It's the reciprocal of the cosine, right? What is the cosine of pi/2? 0, right? Cosine's the x value. So therefore, what's the secant? It's undefined. Okay, so we have a problem there, don't we? Okay, how about the tangent? What's the tangent of pi/2? Since it's y/x, what's it? Okay, we've looked at that like 2 or 3 times today too, haven't we? Tangent of pi/2 is undefined. So we have an asymptote. You see, you're undefined at pi/2. You're defined at 0. If you actually did the tangent of 0, what's the tangent of 0? 0, right? What's the secant of 0? Reciprocal of the cosine, so that's 1, right? You see what I mean? Since you're undefined at pi/2, that means that's why this graph is going to show that you have a vertical asymptote of pi/2. So if I gave you this graph, did I give you this graph? You might write down on here, and I don't know where it is, but it's somewhere around pi over 2. What you have is you have a vertical asymptote. I don't remember how I did the window, but it doesn't matter. Okay, like that. And then this point right here, since both the secant and the tangent of pi over 0 is 0, then that point right there would be 0, 0. Like that. Okay, so that's a graph. And what you're doing is you're looking at analyzing that region right there and see if that converges to some answer or if it diverges. Looks like it converges, but like I said, don't go by looks. Okay, so what we're going to do on this one is we're going to set this up. So where's the problem area, 0 or pi over 2? Okay, that's the one you change to a letter. Problem area there. That's a vertical asymptote. Pick a letter. Let's pick like B. 0, we're cool. So when you do this improper integral, you want to set this up. You want to go from 0 to B of the secant of x times the tangent of x dx. Okay, now here's the whole key, is you want to know what you do with the limit. Okay, so which kind of limit should I use? Left hand or right hand? Left hand, okay. The reason is, real simple, is we're going this way. All of the region is to the left of the asymptote, so that's the reason why we're going to do a left-hand limit. That's the idea, okay? All right, so we're going to set this up as the limit as b goes to what number? Pi over 2 from the left-hand side. Okay, that's how that's set up. So once you get these set up, you're ready to roll. If you got good integration skills, you'll be fine. All right, does that make sense? Okay, it's all where the asymptote is. Okay, that defines whether it's left or right hand limit. Okay, all right, well, like I said, this is a nice simple integral on here. So way back in Calc 1, you should have learned that the derivative of the secant is the secant tangent. So that means we know the integral of that is just the secant. So this would be equal to the limit as b approaches pi over 2 from the left-hand side of the secant of x evaluated from 0 to b. Okay, like that. All right, so let's go ahead and do that evaluation. I'll just keep bringing down the limit so I don't forget. So approaching pi over 2 from the left-hand side. And then this is going to be secant of b minus secant of 0, like that. Now we're ready to just close out and look at that limit. Okay. Well, I've got a unit circle over here, just kind of the key stuff here. So what you're doing on here is, you just go ahead and plug in the pi over 2. So if you're doing a left-hand limit of secant of b, okay, what's happening on this, you just plug that in. Okay, and then this you just do the secant of 0 because you know what that is. So what you're going to end up having is you're going to have the secant of pi over 2, okay, and then the secant of 0. What's the secant of 0 based on this point on the unit circle? What's that? 1, right? Okay, everybody remember that? Cosine's 1. Okay, cosine's the x value. So if the cosine of 0 is 1, then the secant is just the reciprocal of 1, so it's still 1. So that means that's going to be 1 like that then. Okay? All right, now let's think about what's happening on the secant of pi over 2. Well, if you look at pi over 2, the secant, if you were to do the secant of pi over 2, what would happen? That's undefined, right? Okay, remember, the cosine of pi over 2 is 0, right? Therefore, the secant is undefined. Everybody remember that and with me on that? Okay. So here's what happens. Here's another way to look at this then. You don't just say undefined minus 1. That doesn't make any sense. What you do is you think about your graph. It'll kind of help you to remind yourself of this. So you might want to just sketch a little graph on this just to help you remember this. Okay, if we were graphing y equals cosine of x, what hopefully you remember, and if you don't, you go to the unit circle, that the cosine graph looks like that, right? What does the secant graph look like from trig? What did that look like? Had those U shapes, right? So what happens is you would have an asymptote there because the secant is undefined there, and you would have an asymptote at negative pi over 2 because the secant's also undefined there, and what you would have is you would have this U shape right there. So that green graph that's the graph of y equals secant x. Okay, so what's happening on this and what we're doing is we're looking from the left-hand side of this. Well, what's the graph doing? Where is that graph going? What's the value of the secant as you get close to pi over 2? Infinity, okay? So that thing right there is going to infinity. That means the whole thing's going to infinity. So what's the conclusion? It diverges, okay? This did not give you a finite answer. If it goes to infinity, our conclusion is going to be it diverges. Which kind of looks logical, okay? It does go on forever, but sometimes you'll have graphs that look just like that, and because of the nuances of the mathematics, it might go to some particular value, okay? But for now, let's trust the math. All right, any questions? Okay, everybody with me on the setups and why you do left and right hand? Okay, you got to try to learn. If you understand the concepts, you can reason these out so you don't have to memorize so much stuff. Okay, let's do this improper integral. And again, I recommend you do like a graph on this. One thing that, in case you don't know, sometimes students don't know this, the way you would put this one in your graphing calculator is you would go like this. You would go 1 divided by, then you'd have the square root, and you have an absolute value command. If you don't know where that is, it's worth writing down because it shows up some. So let's see if I remember. I think it's under Math button and then the number menu, if I remember right. So try that, Math, and then go over to Number, and then you have ABS. So you'd actually have to put that in like that. Some of you, your calculator will just spell ABS. Mine's pretty fancy, and it goes ahead and gives absolute value symbols. Ooh, okay, so you'd put that in like that, and that's actually an important part of that problem, is that's how that would be put in your graphing calculator. So I'm just doing that to remind you, or if you don't know that, where that absolute value command is in your calculator. Okay, and if you graph that out, you're going to get something like this. Okay, so this is 2. Well, what's happening at 2? Okay, you're undefined at 2, right? So the function is undefined at x equals 2. You can do that without a calculator. You can tell you would have a 0 denominator, correct? So you have a vertical asymptote at x equals 2, all right? Now, if I zoom in on this graph a little bit here, you might want to just make a note to yourself that, yeah, we have a vertical asymptote right there. Okay, now what we have in this situation is we have 2 regions. All right, and anytime that vertical asymptote is in the middle, you got to do 2 integrals. You got to do one integral that's going to be a left-hand integral, and then you got to do one integral that's going to be a right-hand integral. And then you want that 2 to be like where your variable is. So let's get this set up. The whole key is the setup to these problems, and once you do that, you probably will be okay if your integration skills are good. Okay, so I'm going to break this up like this. Okay, first of all, the problem area on this, what we're going to do is we're going to start it, we're going from -2 to 6. So we're going to set this up like this. We're going to go -2. Let me erase that so I have a little bit of room. We're going to integrate from -2, and then we're going to pick something there. Okay, we got to do like a variable there, and then that's going to approach 2. So we're going to do dx over absolute value of x minus 2, like that. And then the limit is, b is going to approach 2 from which side? Left-hand side, right? Okay, so see, the thing is we're going from -2 from there until we get to the asymptote. Okay, does that make sense? Okay, now let's do the next one. Okay, now what we do is now we're going to do this. We're going to go from where to where? See, B is what we're defining to be the vertical asymptote. So you're going to go from B, you can use the same letter if you want to, it doesn't matter. Okay, and then we're going to go to 6, like that. Okay, or you can do a C. I'm going to do a C. It doesn't really make any difference, but I'm just going to do it like that. That's the way a textbook does it, but it doesn't really matter. Okay, and I'm going to do dx over square root of x minus 2. Now, what's your limit going to say? How's the limit going to go on this one? Our letter is C, right? And how's it going to approach? From the right-hand side, okay? So you want to go approach 2 from the right-hand side like that. So that's how your integral is going to go, is like that. Okay, is everybody okay with that? Okay, all right. Just look at the diagram, will help you see that a lot. You got a left-hand, you got a right-hand limit. And the asymptote's always where that problem area is. Okay, so now what we got to do is we got to think about, how we do this integral right here. Well, the thing on this one is, when you have that absolute value, that sort of affects things a little bit on this. So what happens on this one, you got to pay attention to this because this hasn't shown up. This doesn't show up very often in calculus. But what will happen is, see this integral right here, we're looking at this region over here. X is bigger than 2, right? X is bigger than 2. X is greater than 2. So what kind of number is going to be under that radical? If X is bigger than 2, what does X minus 2 become? It becomes positive, right? Agreed? Okay, this is real important on this now. So when you're doing this integral right here, the whole region's there, that makes that positive. Is everybody with me there? Okay, X is bigger than 2, therefore X minus 2 is greater than 0. Okay, that's why. Okay, that's positive. So what that means is, this limit is going to be this. This is the limit as c approaches 2 from the right-hand side of dx, and we just do square root of x minus 2. In other words, we just ignore the absolute value. The reason is because we know that's positive. Tell me if that makes sense, honestly. Is everybody with me on that? Okay. So that doesn't, so you don't need the absolute value. Okay. We know it's positive, so forget it. But if you go over here, this is where you got to be super careful on this, like this. So if you go over and do this one now, okay, think about this. Right now, in this region right here, x is lower than 2, right? Okay, so what would happen if you took a number lower than 2 and subtracted 2 from it? What would you get? Wouldn't you always get a negative number? Okay. Remember, you're doing anything there that's negative. So what's happening here is this thing right here, that is negative. Okay. So here's what you do on an absolute value. And a lot of times students they know absolute value, but they don't know the technical definition. What happens is, anytime you do an absolute value of a negative number, what you do is technically you take off the absolute value symbol and then you multiply it by a negative. You change the sign, in other words, right? So what's going to happen on this one, and this is kind of tricky, you got to pay attention to this when this shows up, is you got to write this like this. That's going from negative 2 to b, dx. Now I'm going to change that sign. So if I have negative x minus 2, isn't that really just 2 minus x? Or just negative x plus 2? You can write it either way. So this thing is going to be written as 2 minus x. Okay? That's a big deal on that problem, that if you aren't careful, you're going to totally forget about that. Okay? Because usually students don't see hardly any integrals that have got absolute value in it. So the idea is everybody solid that you know that since x is bigger than 2, that's positive? So that means take out the absolute value, right? Is everybody okay? Since 2 is less than, or x is less than 2, that's negative. So since it's negative, what do? Well, I change the sign. Okay? Anytime you take an absolute value of a negative number, you change the sign. So that's what I did there, see? So that negative x minus 2 becomes 2 minus x. All right, does that make any sense? Okay.
It's approaching 2 to the left.
Yeah, but the thing is we're looking at x values that are all less than 2. So when we do the absolute value of x minus 2 in here, you're going to get a negative answer. When you do the absolute value of x minus 2 over here, you get a positive answer. Okay? That's the idea. So that's how you have to handle absolute value when you're doing a derivative or an integral. You got to go like that. Okay? So now what we're ready to do is we're ready to go through and integrate this now. And we can do this. This is basically pretty simple U-substitution when you do that. Okay? So what you can do on this one too is you could pretty much reason this out in your head too, I think. I'm going to go over to the side and just kind of think about how one of these would go. So like if you did this integral right here, and if you did like a U-substitution, you would have U is equal to 2 minus x. So you could make that the U, okay, if you wanted to do it this way. And then du is just going to be negative dx. So in other words, negative du is going to be dx like that, okay? Now what I'm going to do on this, since this is a pretty simple integral, is I'm just going to kind of go over to the side, and just on scratch paper over here, I'm just going to work out this integral. I'm not going to do anything with the limits, although you can do that if you want to. So what I'm going to do here is we would have the integral of dx is going to become negative du, and then we would have square root of u. So that would really be negative integral of u to the negative 1/2. So that is negative u to the 1/2 over a half. So that's negative 2 u to the 1/2. And then I'm just going to plug this back in. So u is 2 minus x. Okay? Now you can kind of go over and do simple scratch work if you want to. So basically, what's going to happen on this one is this integral, let's write this as the limit as b goes to 2 from the left-hand side. The value of this integral is negative 2 times the square root of 2 minus x, and then that's going to be evaluated from negative 2 to b. Now, you can do this in different ways, guys. You could change the limits of integration, or you can just, to me, this is a super easy integral that you can even do in your head without U-substitution. So you just get that down, okay? And then we'll take it from there. This one is going to be the same thing. This is going to be the limit as c approaches 2 from the right-hand side. And then this one is going to end up looking almost the same. This one's going to be 2 square root of x minus 2. If you did use substitution on that, that's what you would get. And then you're going to go from c to 6 like that. Okay? So I'm bypassing and not spending a lot of time on the integration. All right, everybody with me on that, okay? What's that? I can't hear you. I'm sorry.
He's asking about not changing the limits.
Yeah, the reason I didn't do that is because I went ahead and did the integral over here. See, I got this. I got u to the 1/2. I just went ahead and plugged the u back in. Okay? Now, you could do that. It's your call. Okay, you can do that either way. Sometimes if it's a simple integral, I just go over the side, do it, and don't change the limits, but it's up to you. Okay, it'll work out the same either way. Okay, so what I'm going to do here is, now we're going to kind of put together our limit. So what we'll have is we'll have the limit as b approaches 2 from the left-hand side, and then this is going to be negative 2 times 2 minus b. Now we're plugging in. Minus, you could also take that negative 2 out. You know, why don't we do that? Okay. Sorry, sometimes I kind of get rolling a little too fast. I'm going to bring that out as a negative 2. And then I'm going to write this as 2 minus b minus 2 minus negative 2. Okay, that's how that's going to go. Okay, now I've already done, then we're going to do the limit of that. Then we go the next thing, we're going to have the limit as c goes right-hand side. Again, I'll just take the 2 out of that. That makes it easier if you do that. So I'm going to say plus 2 times the limit as c goes to 2 from the right-hand side. And then now I'm going to plug in the 6. So I'll have 6 minus 2 minus c minus 2 like that then. Okay? Then I'm pretty close to getting this thing wrapped up then. Okay? So let's see what we got here now. This is going to be negative 2, and what I'm going to kind of do on this now is we're going to go ahead and plug in the 2 from the left-hand side on this. Now what's going to happen on this is if you plug in a 2 there, that's going to go towards 0. So I'm going to go ahead and just do the limit now. So just replace that b with 2. So you have square root of 2 minus 2. Okay, that's going to be square root of 4. I'm doing a few things in my head. Hopefully you follow this. If you don't, just let me know. That's square root of 4, so that's 2, like that. Okay? So I'm plugging in the limit. I'm replacing b with 2 like that. Okay? All right? So now I move to the next part right here. I'm going to have plus 2, and then I'm going to do the same thing. Okay, that is 6 minus 2. So that thing right there is square root of 4. So that's going to be a 2. Then I'm going to plug the 2 in right here. So that's going to be minus the square root of 2 minus 2, like that. Okay, everybody with me what I'm doing there? I'm doing some stuff in my head, just kind of simple arithmetic. And plugging in, so it looks like what I'm going to have here is negative 2, that's 0, square root of 0 is 0, times negative 2, plus 2, times, that goes to 0, 2 times 2 like that. So that looks like what you get is positive 4 there, plus 4, so that looks like that will give you 8. So this particular improper integral is going to converge, and it's going to go to 8, like that. Now that's the idea. The key thing is the setup. I kind of went through the integration kind of quickly there, but that's a simple enough integral that you shouldn't have any trouble with. And then the rest of that's pretty much arithmetic, like that. So that's not too bad. What do you think? Okay, so that's kind of interesting on these problems too, is that this region right here, even though there's a vertical asymptote there, that region still converges to some value. Okay, and the mathematics doesn't lie. Okay, so what do you think of improper integrals? Okay, they're kind of interesting. That's a different idea. And what will happen on this too is improper integrals, when we get to chapter 8, you start looking at what we call infinite series, and then it kind of has a lot to do with this, about the idea that sometimes you can have a sum of an infinite number of numbers, and it can converge to some particular value. That's kind of what we get to, so this relates pretty heavily into that. Okay, so that'll wrap us up for today.